Welcome back to our deep dive series. Today, we're continuing our journey through the Online Encyclopedia of Integer Sequences, the OEIS.
Yes, that incredible resource for anyone interested in number patterns and their connections.
Exactly. And our focus today is sequence A000227. Now, on the surface, it sounds simple enough. It's the nearest integer to $, the base of the natural logarithm.
Right, the d raised to the power. It immediately bridges the continuous world, that smooth exponential curve, with a discrete world of integers.
It does. And that's often where things get interesting. So if you calculate 1 for 1 every $1, $2, and so on, and round to the nearest whole number, what do you get?
Well, a sequence starts 1, then 3, 7, 20, 55, 148.
And just a quick note on indexing, which the OEIS is very careful about. None starts at 0 here. So A0 is 1, which is round $t. A1 is 3, round ABOE2 is 7, round AB2, and so forth.
No, those details matter.
Okay, so far so good. But when you dig into the comments section for A000227 on the OEIS site, you find this really intriguing observation from Stanislav Sikora.
Ah, yes, the connection to another function.
Exactly. He points out that the value 6 equals ever excess $1 is precisely where the function raised to the power of $1 by Keller, well, it's where that function reaches its maximum.
It's a slightly unusual-looking function, sent by the one.
Yes.
It relates 6 to its roots in a way that depends on tangent. And finding its peak lands you right on number.
Yeah. But then Sikora asks a different question. He defines another sequence, let's call it $10. This $10 is the integer, the natural number, that makes that same function by a value as large as possible.
So we're jumping from the smooth, continuous function where the max is at $1 to asking if we can only plug in whole numbers, Tellery, which one gives the biggest result?
Yeah, exactly. You're looking for the peak, but you can only stand on the integer steps.
And this is a classic kind of question. Does the integer closest to the continuous maximum actually give you the maximum value when you restrict yourself to integers?
And what's really amazing here is the observation. Empirically, it looks like the integer dollars that maximizes the discrete function is identical to our original sequence, the nearest integer to our...
Identical. For how far?
Well, according to the notes, this match holds for a very long way, at least up to $0 greater than 24,500.
Wow. That's quite a strong correlation. It suggests the peak of the discrete function consistently falls exactly at the integer closest to the continuous peak in Sellas. That kind of perfect alignment isn't something you'd necessarily expect by default.
No, it really isn't. And this observation actually motivated the creation of a specific test program called A000227 test. The OEIS entry links to details about it.
Okay, so what was the program trying to do? Find a counterexample.
Precisely. It was built to hunt for any value of non-A where the nearest integer to I might differ from 6n, the integer that maximizes k and 1 chi.
And how does it test for that difference? What's the logic?
It's pretty straightforward, actually. It takes A Kellers to be the nearest integer to den, so k will use an. Then it calculates the function's value there, $5 equals k1, k1.
Okay.
And it compares that value val to the values you get at the integers right next door, k plus the dollars and k on dollars.
Ah, I see. So if the function's value was actually higher at k plus dm, or k yumban, then the integer kan wouldn't be the one that maximizes the function among integers. We'd have found a mismatch.
Exactly. It's checking if the peak for the integers has shifted slightly away from the rounded value of $1.
Makes sense. And the results of this test?
Well, they ran it using extremely high precision. The notes mention 30,000 digits, all the way up to $1 and to $4,500. No mismatches found. None at all.
So the empirical evidence is very strong. It really does look like AN's in the same, at least as far as we've been able to check. For number theory folks, this kind of unexpected consistency is really intriguing.
Definitely. And the documentation for the test program even offers a kind of, well, a heuristic argument for why we might not expect to find a mismatch, even for much larger dollars.
Ah, the argument about the shape of the function's peak.
Yeah, something about derivatives and symmetry. Can you unpack that a bit?
Sure. The idea, roughly, is to look at the derivatives of that continuous function, VLN x verse, right at its peak, 6 equals any $. As CI gets bigger, the ratio of the third derivative to the second derivative gets smaller and smaller quite rapidly.
Okay, what does that ratio tell us?
Well, intuitively, a smaller third derivative relative to the second suggests the peak is becoming more symmetric. Think of a standard bell curve. It's very symmetric. If the peak becomes increasingly symmetric and also broadens out,
then the highest point, when you only consider integers, is much more likely to be right at the integer closest to the actual continuous peak.
Exactly. The pull towards k plus Villa 1, or k hello 1, becomes less significant compared to the height at k hand round.
Yeah.
It makes a mismatch less probable.
Got it. So it's a plausible explanation for the observation, but as the OEIS entry carefully notes, it's a heuristic. It gives us a good feeling, but it's not a formal mathematical proof.
That's a critical distinction, yes. Proving it rigorously would be a different, likely much harder task. But the heuristic aligns well with the strong empirical data.
It's also neat to see the OEIS entry mentioning historical references, like tables of the exponential function from way back in the 1930s. Puts the sequence in context.
It does. It shows that understanding $100 and its properties, including how it relates to integers, has been a long-standing mathematical endeavor.
And true to OEIS form, there are cross-references. A euro 000149, which is the floor of 119, the ceiling of $1.
So rounding down and rounding up, respectively.
Right, and even A002160 here, which is the nearest integer to time, it really shows how these ideas connect across different sequences.
Those links are invaluable. They let you jump between related concepts and see how changing the constant or the rounding rule affects the resulting sequence. It opens up avenues for comparison and further questions.
Looking at the keywords for A000227, we see non-negative, easy, because the definition is simple.
Relatively simple, yes.
And nice. And I think nice really captures the surprising connection to the function maximization problem we've been discussing.
I'd agree. It points to an aesthetically pleasing or mathematically interesting property. And seeing the last modified date reminds you the OEIS isn't static. It's constantly being updated and refined.
Absolutely. It's a living library.
So wrapping up on A000227. It starts with the basic concept rounding him or a dollar, but quickly leads to this deeper question about where a related function achieves its maximum value among integers.
And the answer, based on extensive testing, seems to be remarkably consistent. The maximum occurs at the nearest integer to $8.
Which leaves us, especially those interested in number theory, pondering why. Is there some fundamental reason buried in the properties of the exponential function and integer distributions that dictates this incredibly tight coupling?
That's the lingering thought, isn't it? Does
Yeah.
this hint at a principle connecting continuous functions and discrete maximization that's particularly strong for hollow dollar? What happens for even larger dollars, or perhaps for functions based on other constants?
It certainly gives you something to mull over.
It does. We definitely encourage you, the listener, to explore A000227 and its related sequences further in the OEIS. Thanks for joining us on this deep dive.